Isomerism, we have found that coordination compounds exhibit isomerism. If the question comes why the coordination compounds exhibit isomerism, you have to say that coordination compounds are formed by coordinate bondings between the metal and ligand. So any compound which is having which is covalently formed, they will show because they have a proper or fixed direction in the space. So just like organic compounds, we will find coordination compounds will show two types of isomerism. Broadly, two types of isomerism are the structural isomerism and stereoisomerism. The structural isomerism arises because of the bonding activity, and the stereoisomerism forms due to the different orientation in the space. Structural isomerism of the coordination compounds can be classified into four categories. They are ionization isomerism, the ionization isomerism occurs where you find that the counter anion can act as a so the counter anion replace the coordinated ligand inside, and by which they form the ionization isomers. Then second category is the linkage isomers, linkage due to the embedded. Then comes the hydrate isomerism or solvate isomerism. In these cases, solvents are being coordinated to the central metal atom, and counter anions, they replace their solvent, they come out and remain in the molecule as the form of molecule of crystallization. Then the coordination isomers. Coordination and anions are coordination entities, and between them the exchange of partial or complete exchange of the ligands. All right. Then comes the stereoisomerism. Stereoisomerism, you know, stereoisomerism can be classified into two categories. They are the geometrical isomers and the optical isomers. We are going to discuss here three types of structures. These are tetrahedral, square planar, octahedral complexes. Tetrahedral complexes do not exhibit any type of geometrical isomers. Even if the direction of the ligands in the tetrahedral complexes changes, their distances from the other ligands remain same. Due to that, we find the tetrahedral complexes will not exhibit any geometrical isomers. Now we'll go to the second one, the square planar complexes. We find square planar complexes are formed by metal atom with four ligands. So I told you that MA4 and MA3B do not show geometrical isomers. So geometrical isomers can be shown by MA2B2, B, C, they show geometrical isomers. When the similarities are on the side, then it will show C isomer. Similar ligands are on the opposite side, it will show trans isomers. Okay. Among them, I told you molecule you have to be very, very careful. Is called the dichlorido platinum 2 compound. Cis isomer is being used as a medicine for treatment of cancer, which is known as cisplatin. So take care. After that, we will go for octahedral complexes. In octahedral complexes, metal atom, metal ion is being coordinated by 6 ligands. So MA6, MA5B do not show any type of geometrical isomers. So geometrical isomers are being shown by MA4B2. Now, in that case, ligands can be unidentate or ligands can be bidentate. So depending upon that, you will find them to show one or more than one geometrical isomers. Every molecule is going to show only one cis isomer, and geometrical isomers will be more than. Now, then let us go for the MA3, B3 complexes. In MA3, B3 complexes also, they are supposed to show us cis and trans isomer, but we find we have a different nomenclature. What is the nomenclature? We find if the three are placed in the same face of the tree formed by the hands, we call them as facial. And if they're along the axis, then we call them as meridional. B3 complexes. The isomers do not we describe them as cis and trans, we describe them facial and meridional. Then we go for optical isomers. So one thing you should remember, cis isomers show us optical isomers. Trans isomers, they do not show us any optical isomerism. Why? Because trans isomers have plane of symmetry. We have organic chemistry. Only the asymmetric molecule can rotate the plane of light. Isomers, we have mirror plane or planetary by which the rotation of the light does not take place. Very serious mistake which I have done, I forgot to tell you. The square planar complexes, any type of square planar complex, they should not show any geometrical isomers. Why? Because planar complexes have plane of symmetry. Please write down this one. Please write. Right. Square planar complexes irrespective of any ligands do not show Optical isomerism. Because they have plane of symmetry. Plane of symmetry. Okay, plane of symmetry. See, the name itself is square planar. So the ligand and their central metal atom or ion are in the same plane. So because of that, they have a planar symmetry. Okay, so this is the summary of this thing. Now, what are the type of questions you can expect? First of all, you can have questions in the form of their name. They will give you one formula and they may ask you to the IUPAC name of the ionization isomer of it or linkage isomer or hydrate isomer. So mark will be 1. But in that, write it in 2 parts. First, you write the molecule. After that, you have to write the name compound. So if you write the name of the molecule which is given to you, you will get 0 because they have asked the isomer. So please remember, this is a very important thing that you should know how to write isomers. Formula of the isomers, and writing the formula of the isomers, you have to write their IUPAC name. Second type, they will simply ask you what are isomers of the following molecule. You have to write the isomers of the following molecule. It's structural or it may be stereoisomers. Or generally in entrance exam, they may ask you how many types of isomers are possible. So please remember, types of isomer possible is that every mole has 1 cis isomer and trans isomer may be 2, or you may have more than 1 trans isomers. So on the basis of that, you should be able to write the structure and write it everything. All right. So these are the questions possible from the isomers. Okay. Now we are coming to the more theoretical part, the coordination compounds, about their bonding. Okay. Coordination compounds. See, initial theory which is being given to us by Werner, it was explain the bonding, because he did not mention anything about bonding there, because in those days he has done it in the beginning of the 19th century. So those days concept of people did not have clear-cut idea about the electrons also. All right. There cannot be any question of any is present in coordination molecules. Usually with the bonding, people could different theories about the coordination bonding. So the bonding in the coordination compounds are being, these theories are gradually being extended and modified. Right? So it is not a fault of Warner. Warner only mentioned that coordination compound contains two types of linkages. Please remember the word linkages. He did not even mention the word bonding. One is called the primary linkage, which is ionizable. That is, if you dissolve it in water, they separate. And the second one was secondary linkages, where do you find these species, even in aqueous solution also, they do not break down from their main molecule. So we cannot bonding from the Warner's theory. Okay. Anyway, so let us write down limitations of Warner's theory. Okay. External nature means they have a fixed position in the space. কি বলে ঘুমাই গেছে ঘুম ভাঙছে না বলে না না সবদিন থাকে না I told you now, if you, after finishing, you tell me, finish, otherwise, I will not write anything more. Okay. So now, we'll see different theories are being put forward to explain. The first theory was proposed by Linus Pauling in the form of valence bond theory. Because Linus Pauling is being, he has only studied the in a chemical molecule, and he has given the concept of hybridization. So valence bond theory deals with the hybridization. All right. So now we'll go for valence bond theory. Excuse me. Hello, buddy. Theory of coordination compounds. See, now already I have sent you this note. So in that case, I'm not going to discuss, because all the things that I'm going to write, it is there. Word by word will be the same thing, because this is the note already I have sent it to you. So let me explain you first here. See, when we take a central metal atom or ion, then in that case you find the ligand molecules are surrounding them. Okay, now in that case, the central metal atom, first they make their sp and d orbitals available, empty d orbitals available for bonding, empty d orbitals. Okay, so in that case what we'll do, if the d orbitals, what are the number of the d orbitals that is required for bonding, if this is not, or if all of them are not free, then they transfer their electrons to other d orbitals and make them available. Just like that, suppose you have invited some people in your house, and depending upon the number of people that you have to make their sitting arrangement. So if you find the number of chairs in your dining table is less, then in that case you will bring some chairs from other room. You make your dining place exactly on the number of the people that they are going to sit there. So similarly, in case of the central metal atom, they utilize their valence shell, s orbital, valence shell p orbitals. Now when it comes to the it comes to the d orbitals, either they take the inner d orbital or they take the help of outer d orbital. Depends upon that whether it is free or not. If this inner d orbitals is not free, it is containing electron, they take the help of the outer d orbitals. So when this type of complexes are being formed by the hybridization of the outermost shell s and p orbitals and inner d orbitals, this type of complexes are called inner orbital okay. And if it is like this, that inner d orbitals could not be made free, then they take the help of the outer d orbitals and they form the complex which is known as outer orbital complexes. That is, according to valence bond theory, the complexes are being formed by the overlap of the field orbitals, say it is ammonia, with the empty hybridized orbital of the central metal atom or ion. Okay, this is empty, this is filled. So, see, this is the way the bonding is going to take place. All right. So it depends upon that how many ligands are going to bind. If the 4 ligands are going to bind, then they are going to form 4. Okay. So depending upon the number of ligands that is going to form, so in that case you will find if it is 4 ligands are bonded, then in that case you know that we can have we can have 4 hybridized orbitals can be made available by sp3 hybridization. That is tetrahedral arrangement will be there. Or we can have square planar complexes where it will be S p to d orbitals. Now, if 6 ligands are available for bonding, in that case, it is going to form octahedral complexes. So, octahedral complexes, if you go by this, in that case, it will be NS, then, sorry, if you go by this one, then you will have here sp3. So it's inner orbital now. So this will be here. It will be d2sp3, which is the inner orbital. And if it comes from the valence shell, then you will have here now sp3d2. Both of them give us octahedral complexes, but only thing is that it depends upon from where the d orbitals come. Will it come from the inner orbital or will it from the outer orbital? Okay. So this, whatever I have written it for you, please read from there. Moment you read, you will be able to understand. Now, that is, we have seen in the valence bond theory, it says that the metal ligands bonds are being formed by the combination of the filled orbital of the ligand with the unfilled hybridized orbital. So the hybridization occurs by the mixing of the outermost shell S and P orbitals along with the d orbitals of equivalent energies, or it may be the inner orbital of equivalent energies. They will hybridize, and after the hybridization, the empty hybrid orbitals will overlap with the filled orbitals of the ligand, leading to the formation of the coordinate bonding. Yes, because the molecules are formed by the coordinate bonding, so these are being called the coordination compounds. Okay, now in the process of this type of arrangement of electrons by the process of hybridization, you may find that the some of the orbitals may have unpaired electrons. So in that case, these molecules will behave or will be attracted by the external magnetic field. So they will show us paramagnetism. So it could be paramagnetic in nature. And if they have field or they do not have any unpaired electrons, so in that case, you'll find they will be weakly repelled by the external magnetic field, and it will lead to the formation of the diamagnetic complexes. Whatever I'm now telling now, you may not be able to understand. So I don't want to waste the thing by writing the same thing which I've already posted to you. So we'll start with examples. Moment, I'll start with examples. Then things will be very, very clear. Okay. Try to understand that. Valence bond theory is very easy. Only thing that you have to remember is the first series of transition metal, that is from scandium to zinc, their atomic number. Okay. So now, the first example that we are going to do is coordination compounds with coordination number 6. You know what is called coordination number? Coordination number is nothing but the number of ligands which surrounds this central metal atom or bonded to central metal atom through sigma bonds. Please remember, if it is bonded through pi bond, then we do not consider that bond. Right? So, coordination number is that it is the number of the ligands, monodentate ligands. Number of the monodentate ligands which binds to the central metal atom or ion through sigma bond. Okay? So it's 6. So we know these are called what? It is. What do we write now? This is what? Octahedral complexes. Okay, let us take. Okay, now here. Before we go for this one, only one series you have to remember now. Maybe after 2-3 days, after we have practiced, then you will find you will not be able to forget this one. So I'm going to write a series of ligands in order of the strength. This one you only have to remember. Okay? So, arrangement of ligands in increasing strength. So when you say increasing, always we start from right. If you say decreasing, we start from left. Okay? So I'll write from here because, okay, say here. It is carbon monoxide. Can you see?
Yes, sir.
Then cyanide. Then En, ammonia. There, I'm writing only those ligands which are common with your textbook. There will be hundreds of ligands. So I'm not going to mention to confuse you. See, basically, I was a very weak student. And my memory was also not that sharp like you people. Huh? Okay. So I have learned chemistry in the way which I can remember. So first you write, then I'll explain how to remember. Anything which is convenient for you, always learn in this. Everything may not have, everybody may not have a photographic memory, na? So you learn according to your convenience. You know which technique you should follow.
Yes, sir.
Okay, now see here, very interesting. In this case, all the left-hand side alphabets are the atom which binds with the central metal atom. It is here, it binds to carbon, binds through carbon, binds through nitrogen, binds through nitrogen, binds through, here of course it binds to oxygen, here also oxygen. See, this entire series being arranged in order from low electronegativity to high electronegativity. See here, the electronegativity increases in this direction. Okay, so it is arranged on increasing electronegativity of bonded atoms of the what I write donor atoms of the ligands. Say, take the example. We know in our periodic table, negativity increases from left to right. Okay, so electronegativity. What do you find here? Suppose I start from this. What should I say here? Lithium, then beryllium, then boron, then carbon, then nitrogen, then oxygen, then fluorine. Is it not like this? Electronegativity is like this. Of course, here I put fluorine, chlorine, bromine, iodine, that is something else. So this one. Did I make any mistake? Yes, I have made a mistake. Halogens, what do you find here in this case? In this case, you find if you compare carbon and if you compare nitrogen and if you compare fluorine and oxygen, see here. In this case, what do you find? Yes, because they have less electronegativity, lesser electronegativity, lesser the electronegativity, better will be their electron donating properties. See, suppose you, for any cause, you want to raise some money. So you go to your locality for collection of money. Looking at the size of the building, you cannot ascertain that that person having a very big building, so he will donate more money. The other person is having a single-story building, he will donate less money. No. The donation for your cause depends upon not the size of the building, but the feeling of the person for your cause. Okay? If you go to a very big building waiting for half an hour, then the person comes, talks to you for a long time, then he gives you 100 rupees. And if you go to a person, okay, with a smaller size of building, moment you tell him your cause, he did not ask you so many questions, he gives you more money. Why? Because the person, first person who has given you less money, that is, he has more affection for the money, which you can otherwise say that he is a stingy person. Okay? So in case of atom, if the electronegativity is high, he doesn't want to part his electron with others. So it will be a weak donor. And those where you find the electronegativity is less, they will be a strong donor. Okay? So what do you find here? We have written strong ligands means what? They will donate electron faster. And in this case, you find there high electronegativity. So higher the electronegativity, weaker will be their electron donating tendency. So because of that, we call them as strong ligands, and these are called weak ligands. So if you go for raising money, you will find these are large-hearted donor, and these people are stingy. They don't like to give you. So on the basis of that, if you arrange, then you will not never forget it. Only thing is that this atom I will convert into.
So in that fluorine will be the weakest now, sir. Fluorine
No.
will be the
Again here why it is we have arranged like this, you are perfectly correct if you go by this theory. But thing is that sometimes the theory changes because it depends upon their size. If you go for fluorine, it is a very strong, having it's the highest electronegativity. It should be the weakest ligand. Correct, you are perfectly correct. But it depends upon their size. Size of the fluorine is smaller. Size of the iodine is bigger. In that case, you'll find if you try to introduce very large size iodine atom, the compounds will not be that much stable. Understood now? So here, even the fluorine is having highest electronegativity, we find because this is the arrangement of increasing strength. So in that case, it is disadvantage is that it is having highest electronegativity, but it is having the greatest advantage of its very small size. So many fluorine can be accommodated in the coordination compound. Clear? So could you understand this one? Please write down. Now, this one this series has a name here. This will discuss again in another theory. This series is called electrochemical series. Actually, this comes in other theory. But the examples are then valence bond theory. Because of that, I told you. And after that, I tell you why the series are being arranged in this way. This I have told you just to make you understand. Is not, you will not find in any book. I find that this is the best way to remember the series. So let us take the first example. So let's take the first example of this hexamine cobalt 3 I. So here we are going to write. See, this is the electronic configuration we are writing. Electronic configuration of cobalt. Cobalt is 28, not 28, 27. So cobalt is 27. Okay, I need not write 1s to 2s to write this. I'll write here with air. Please remember there, argon has 18 electrons. Its cobalt belongs to the first series of transition elements, that is, we call it 3D series. So we'll have, after that, we'll have here 4s2 and 3. See now, plus 2 means 18 plus 2 is 20. So if I subtract from 27, it comes to 7. This. Now I have to find out the oxidation state of cobalt. Of cobalt. What is the oxidation state of cobalt here? Now we know what is the oxidation state of cobalt. See here. Here I write A plus 6B equal to plus. We know ammonia is neutral ligand. So 6 into 0 is plus 3. So A is equal to plus. So what do you find oxidation of cobalt is here plus. All right. Means what? Here cobalt exists as cobalt 3 plus. So what will be its electronic configuration? Yeah, we know even though the electrons after filling 4s2, after that it goes to 3D. But when the loss of electron takes place, first electron will go from the outermost shell followed by this. So 3 electrons are lost. So 2 from here and 1 from here. What should I write now here? I'll write now 3d6 4s0. So this is the electronic configuration. Okay. So now I'm going to write it in box diagram. I'll write here now. The plus, I'll write here 27, 27, and here I'll write below. X side, sorry, ground state. Okay, so I'm only going to write this. I'll not write here. Okay. So I'll write here now. 4s this is 4s 4p, and here I'll write 3d. 3d. 4s you don't have an electron. 4p also you don't have an electron, and 3d is 6. So I'll write here now 1, following Holmes rule 1, 2, 3, 4, 5, 6. Okay, now see here. Ammonia is a strong ligand. So when the ammonia will start approaching this way, due to repulsion, what will happen? See here. This electron from here it will come. This electron will from here will come. Okay. So I'll write now here. See, now this is not a ground state phenomenon. This is excited state because energy, because of the energy. So what should I write now here? This. Sorry, I have done a mistake. 3D I should write inside. Sorry. I have to write in order of energy, na? Sorry, dear. So this. 4s, 4. All right. So this is sorry. This will come here. This will come. Okay. See. So some diagram is being given in your book. Somehow I disagree with this. So this is paired. This also get paired. This two has become empty now. 3D, 4s, 4. How many ligands are there? 6. For 6 ammonia molecule, you require 6 empty hybridized orbital. See here. So from here, this 2 plus this and this you will join. In your book, they have written like this. Something like this. No, I don't agree. Why? Because hybridized orbitals have completely separate energy and their orbital shapes are also different. So I cannot put it in your book as they are written. They are written like this. Okay? So I do not agree with them. There should be some logic. Just for our laziness, I cannot change the theory. So now what I will write down here? 3 plus, here I'll write here hybridized. These 3 will separate. These are unhybridized. So their energy and shape will be different. And these will have the hybridized. We know as many orbitals you hybridize, you are going to get same number of hybridized orbitals. So 2 plus 1, 3, 3 plus 3, 6. 1, 2, 3, 4, 5, 6. Okay? Now, in that case, we know that hybridized orbitals energies are different, shapes of the orbitals are different, so name also will be different. So what will be the name? Say here. How many I have taken from here? 2. So I'll write here D. I am writing in order of energy. S. How many P? 3. 6. Here we have taken the D from the 3 and S and P from the outermost shell. So this is inner orbital. See, now your hybridized, empty hybridized orbitals are ready. Now the ammonia will come and donate 2 electrons each. So when they come and donate electron, in that case, it no longer remains as cobalt ion. It has already formed the complex. Okay. So now see, each ammonia molecule has given its lone pair. I have put star just to indicate that these electrons and these electrons are not same. See, I'll write now here D2 sp3. Now, what is our conclusion as per valence bond theory? Conclusion is 1. That is, hexamine cobalt 3 species is an inner orbital complex. Does it have any unpaired electron? No, it does not have. So what will be its magnetic property? That it is diamagnetic in nature. Any question? Hello? Anyone who could not understand? Hello? Any question you have? What happened? Why there is no reply? Is it clear? Understood?
So can I explain again that one after electronic configuration? So can you please explain again after that one after electronic configuration?
From here?
Up there.
Yeah.
Yes, sir.
See, why should you write such a long atomic configuration? We know that the first series of transition elements, that is 3D series, starts after argon. Okay. So instead of writing 1s2, 2s2, 2p6, 3s2, 3p6, why should I go up to this much? When I write argon, my problem is complete. See, what? Look here. What should I write? Should have written 1s2, 2s2, 2p6, 3s2, 3p6. Okay. How much it comes, yes? Is it not 18? Huh? So instead of writing so much, I've done argon because after argon only that third series starts. Understood?
Yes, sir.
Then any other question? Please remember always the strong field ligand will always adjust electron inside. And if it is a weak field ligand, it will not go for any adjustment because it is weak. It cannot supply electron. Because when the strong field ligand supplies electron, there is repulsion. Due to repulsion only, electron moves to the within the orbit, which are where, because we know these are all orbital here. 3D XY, 3D ZX like this. All right. So each of them can keep 2 electrons. So the space is there, immediately they go back. All right.
Yes, sir.
Now, I'll take now 2 minutes time. See here. Let me change the situation. What is the situation here now? Hexa cobalt 3 plus. Okay. So up to this much is same. Now see here. Water is a weak field ligand. Yes, water is a weak field ligand. Now in that case, because oxygen is more electronegative, oxygen will not try to liberate electron immediately. So there will not be any repulsion. So in that case, what will happen? See here. This is 4s, 4p, 4t. Now water is weak field ligand. So in that case, you will find water molecule cannot adjust the electron. But the complex has already been formed. It is already water without disturbing this electronic configuration. It could get 6 hybridized orbital. So how it is possible? It is only possible because that water has utilized these orbitals from the 4D. So is it not from the same shell? This outermost shell, this outermost shell, this also outermost shell. So in that case, what will happen? That it is going to borrow 2 orbitals from the valence shell, d orbitals. See here. So what will write now here? I'll write here cobalt 3 plus hybrid. Not hybrid. I should not write hybrid. I will write hybridized. They are also please change. This is not hybridization, hybridized. So what will happen now? It is not going to disturb this. See, it will remain here. So it will take 2 electrons from 2 orbitals from here. Okay. And out of 5, it has taken 2. So 3 will be here. What should I write now here? 3D. See here. Now I have to write alphabetically. S, P3, and I have taken 2. D2. And this is 4. Now,
So alphabetically.
Yes.
You said we have to write alphabetically.
Yes, alphabetically means we have written in order of energy. Energy of S is less than P, P is less than D, D is less than F or not?
Oh yes, sir.
Yes. What the question alphabetically? Okay, now see here. So now this 6 hybridized orbital water is going to coordinate. So we'll get now here 3 plus. So what should I write now here? Yes. After that, I will not write this. See here. So you have got this. Now, what will be your conclusion? What will be the conclusion now? Conclusion is hexa-aqua is an sorry sp3 d2, this is 3, is an outer orbital complex. So this is one. What is second? Low. It has 4 unpaired electrons. So what should I write now here? It is strongly paramagnetic in nature. Now suppose in your exam they may ask you to calculate its spin magnetic moment. So what should you write now here? Magnetic moment that you know, mu is equal to what? Root over n into n plus 2 bm. So how many you have here? 4 into 4 plus 2 bm. So the value that you get, you write, finish. Okay. So rest I'll do in your subsequent days. I'll try to do as many examples as possible, and I have given plenty of examples in your book. Okay then, bye for today. Please call.